preliminary. You have notes and references from this week back there. Also, the syllabus that I handed out the last few weeks. Al pointed out that I was off by one day. So if that really bothers you, I have corrected ones back there. And so I did that for the OCD folks in here. So by the way, I'm one. So I'm proud of it. So today we're talking about the laws of nature and the beginning of time, but I wanted to kind of talk about some things from last week. So last week we talked about truth, how in the concept of absolute truth, that there is a such thing as absolute truth, is kind of only makes sense within the context of the Judeo-Christian worldview. And of course that concept, belief in absolute truth, is what really one of the things that enables science. So I looked in the Gospel of John. We talked about that one verse in John 14 where Jesus says, I am the way, the truth, and the life. And we talked about how Jesus, really being the Word of God through whom the world came into existence, is the reality, in a sense, ushers forth from him. And so you really can't make sense of reality apart from him. So if we love the truth, we will come to Jesus, and if we know the truth, we will, if we know Jesus, then we will know the truth. And this is what it says in John chapter 18. Paul is, or not Paul, but Pilate is asking Jesus, because the accusation against him is he claims to be a king. And so he says, so you are a king, said Pilate. Jesus answered, you say that I am a king. In fact, the reason I was born and came into the world is to testify to the truth. And everyone on the side of truth listens to me. And then in John 8, he says, if you hold to my teaching, you are really my disciples, then you will know the truth, and the truth will set you free. I like to say this is one of the most misquoted verses in the Bible. You see it, I think, on the wall of the NIST, in other places, and the idea is, if you know scientific truth, and then it'll set you free. But the context really is, if you know Jesus, if you're his disciples, then you will know the truth, and the truth, that truth, will set you free. So nothing really makes sense apart from Jesus. And also, as you go through the Gospel of John, another concept that's repeated often is Jesus is the light of the world. Come to the light. And so this equivalence between light and life and truth. And Jesus said, I'm in the world just a little bit longer. I'm the light of the world. I'm here just a little bit longer. Come to the light. Believe in the light so that you may become sons and daughters of light. And so he has that invitation to us that we can come to him. He is the light, the giver, the source of all light, and we become children of light when we come to him and put our faith in him. And I think that's really cool. So today we're going to get a bit technical. I guess we're going to do that every period, but I wanted to talk about numbers. Numbers are actually very important in the Bible. In fact, there's a whole book of the Bible called Numbers. But oftentimes the authors of the Bible noted how many people of each tribe and each clan returned from exile, how many things of each kind people offered to the Lord, and some numbers had special meaning. The number 7 is repeated often, has some symbolic meaning. The same thing with the number 12, and then you get to the 144,000, which is 12 times 12,000. Saw those numbers in the Bible, but numbers in ancient Hebrew are actually spelled out. They didn't have digits that represented numbers. Instead, they had words. So you had the word 10. You wrote out 10. You wrote out 9. You wrote out 8. So you can see that would be a bit awkward. So Romans, they came up with the Roman numeral system, which actually we still see today. So this represented each numbers with letters rather than words. So the letter M represented 1,000, C represented 100, L 50, V 5, and I 1. And so they broke things up into 1s, 5s, and 10s. So that number right there, so that's 1,000 plus, since 100 is before 1,000, that's actually 900, so 1,950, but the I comes before the V, so that means you have one less than V, so that's 4. So 1954, my birth year. So that's how Roman numerals worked. So you can understand why maybe the Romans weren't, big into, abstract math and all that kind of stuff, although they were great engineers. So, and then the number system we have today is actually, they're called Indo-Arabic numerals, and they came to Europe in the 10th century, so it'd be the 900s AD. And so they came from the Arab world, which in turn got them from India. So this was the ascendancy of the Arab Muslim empires, and they were conquering all sorts of people and stuff. And so the Western world came in contact with the Eastern world and India through the Arabs. And so that we get the Arabic numerals. So the digits went to special symbols that represent each digit. And then the decimal system, where you have a ones place, tens place, hundreds place, and so forth. And it became a very convenient way of representing numbers, and was a very powerful system that they brought to the West. They also brought the number 0, which Al was complaining about last week. 0 is a special number, and we'll talk about that in a little bit. It's good, and it has its good side of the light side and the dark side of the number 0. So we'll get into that a little bit. So, and all I can say is praise God for Arabs and Hindus, right? So the price of gas the other day was $3.439 dollars per gallon at Shell and Berea. Now, to write that in Roman numerals, you see it down below. The Romans actually used special symbols for fractions, and they had weird fractions. So that's a representation for 3.439 in Roman numerals. So you can imagine the tumblers trying to roll by on the gas pump as you're monitoring the price of gas. All right. So now we get the scientific notation. So scientific notation is a way of representing numbers that are very big or very small in a compact way together. And so it's actually a pretty cool system. So, how do you deal? You have these big long numbers, and how do you deal with all those pesky zeros that are following them, or pesky zeros preceding them? If they're fractions, well, you represent them in terms of powers of 10. So the number 1 is 10 to the 0. 100 is 10 times itself twice, 10 times 10, right? So, and 1,000, 10 times 10 by 10. So that little exponent, that little small letter, shows the number of times you have to multiply 10 by itself to get a certain value. So now if you want to represent the number 314, you can write it as 3.14 times 10 to the 2. And it's the same number, okay? Happens to be 100 pi, but we won't worry about that. Okay, now how do you do fractions? Well, there you have a negative number in front of the exponent. In fact, that's the same thing as dividing by the number to a positive exponent. So a tenth is 10 to the minus 1, a hundredth is 10 to the minus 2, and then you have milli, micro, nano, and pico. So on the one side you have thousands, millions, billions, trillions, and on the right side you have milli, micro, nano, and pico. So you've heard of milligrams, right? So you tend to get medicine in terms of milligrams, so that's in terms of thousandths of a gram. And then you have micros, so you can get into micrometers, use that maybe in machining if you happen to be machining in metric. Nano, now when you get down to nano, so that's billionths of a meter, you're getting into terms in terms of the wavelength of light. And then the pico, which is trillionths of a meter, I think you're getting down to the size of atomic particles and so forth. So anyway, so fraction 0.034 is the same as 3.14 times 10 to the minus 2. Okay, who cares? You're not going to use this in cooking, okay? But in engineering and science, it's very valuable. If you're trying to be that accurate in terms of milligrams when you're making, pounds of food, that doesn't make any sense. Who cares? As my father told Jenny, which was liberating to her, it says, don't use measuring devices, just throw it in, use your creativity. And she found that very liberating in cooking. So it means we never have the same food twice. All right, so here's some examples of big numbers. So you've probably heard of avocados. Oh, no, it's Avogadro's number, right? So it turns out to be the number of protons and neutrons in a gram of matter. So if you have 3 grams of fat and you want to know how many neutrons and protons you are that come from the fat, how many you're eating, you multiply that number times Avogadro's number, which is 6.2 times 10 to the 23rd power. So again, you're not going to use this in cooking, but if you're a chemist, you're going to use this all the time. Avogadro's number is very, very important in chemistry. Right? What about a light year? Distance that light travels in a year. So how big is that? Well, light travels 7 times around the Earth in 1 second. It travels 3/4 of the distance to the moon in 1 second. How far does it travel in a year? That's what a light year is. Well, it travels 5.879. We'll say 6 times 10 to the 12th miles in 1 year. So that's 6 trillion miles in a year is how far light travels. Very important if you're dealing with astronomy. Okay? So what about the diameter of the visible universe? It turns out to be 93 times 10 to the 9th light years. So it's 93 billion light years from edge to edge of the so-called visible universe. And that's equal to 550 times 10 to the 21 miles. So that's some use of the scientific notation. Okay, now we're going to talk about some really big numbers. You thought these were big? Okay. Google. Right? Turns out Google got their name from Google, but they misspelled it probably maybe so they could copyright it. Okay, and it's 10 to the 100th power. So, which can also be written with a double exponent, 10 to the 10th to the 2nd power. The same thing as 10 to the 10th, and that's a Google. All right. Well, why on earth would you use a number like that? Well, it turns out that the possible physical events in the universe, in the history of the universe, assuming that it's billions and billions of years old, I'll get into that in week 9, okay? But there's a 10 to the 116 power possible events in the history of the universe. And they base that on, I have a reference in the notes, they base that on a number of atomic particles in the universe, guesstimated of course, times the number of possible interactions that you could have, say in a second or a picosecond or whatever, times the duration of time since the origin of the universe. So it seems like an awful lot of events, but it turns out you can write it on a longhand on a single piece of, 2 lines on a piece of paper. You can write that number out longhand. So I have some examples of really longhand. So you get to 10 to the 10 to the 24th power. That's to write that number down longhand. You would take all the Library of Congress multiplied so it covers the entire surface of the Earth. So who cares? All right. Okay. All right. We'll see in a little bit. All right. So really small numbers. So really big numbers help you to visualize really small numbers. So think in terms of probability, right? So the odds of being struck by lightning during your lifetime is written as 1 over a very large number. So it's 1 in 15,000. So the chance of you dying, not knowing anything, the chance of you dying from a bolt of lightning is 1 in 15,000. So if you have 15,000 people that you know, if you don't know anything else, one of them is kind of likely to die from being, struck by lightning. So fortunately, that's much bigger than the size of Grace Church. So anyway, but eventually we may get up there. But if the person is in the habit of hugging light, flagpoles during thunderstorms, the probability goes up. So now you have some knowledge that changes the odds a lot. Okay. So what about Powerball? So if you play Powerball, so Powerball, combination of state lotteries, turns out the tickets that are bought for a Powerball is on the order of the population of the United States. So this becomes very popular. Obviously, some people are buying a lot of tickets, okay? But the odds are extremely small of winning, all right? So you could buy 100,000 tickets, right? And you still have 1 in 3,000 chance of winning, okay? And that's a lot of money. So, okay, well, I'm not going to do that. I'm going to buy 1 ticket per drawing for 50 years, all right? That increases my odds a lot to 1 in 40,000. So you have a 1 in 40,000 chance of winning, but how much is it going to cost you? $15,600. So that's why I like to term the lottery as a tax on stupidity, okay? So you're just giving your money to the state, okay? That's what you're doing. It's a tax, and you're not going to get anything out of it. So the problem is somebody wins, right? And so that gives us hope that maybe we're going to win, but no, you're not going to win. All right. Okay, so that's probabilities. Now, what about some really low? Talked about one. Yes.
May I share one example of a small number that's important in biology?
Okay.
In early cancer detection, we talk about 1 e to the minus 5 a lot. And that is one piece in 10,000, right? What that is if you want to be able to detect in blood early signals of cancer, that's the type of sensitivity you have to have when you're counting molecules. So if you measure 10,000 molecules, a very early stage cancer is putting one cancer molecule in those 10,000. And it's super difficult to find one out of 10,000.
It's a needle in a haystack, right? Yeah. All right, so now we're talking really low odds. So that's 1 over a Google, right? Or 1 over a Googleplex. So we talked about a Googleplex is 10 to the Google. Right? So that's extremely low odds. You're going to see that number in this presentation, okay? And it has to do with the fine-tuning of the universe. The fine-tuning of the universe is on the order of 1 part in Googleplex, which is absolutely wild. Okay. All right. Now we'll get into Al's zeros again. So what is a singularity? It's when you do a no-no, which is dividing by 0. Don't divide by 0. What happens is if you divide by 0, your program blows up. Yes?
My understanding is that only people in Michigan divide by 0.
Okay. Did they lose, by the way? Or no, that would be Notre Dame. I don't know who won the game. Anyway. Okay, so to illustrate, so this is called a singularity. When you get to a point in your equations where you end up dividing by 0, and you're going to see singularity, the idea of singularity. So if you look at this graph, okay, so you have x in the horizontal axis, y in the vertical axis. So what you're doing is you're plugging in different values of x, and you're seeing where the y is in that equation. So 1 over x. So you're plotting 1 over x versus x, all right? So if x is 1, 1 over x is 1, right? That's easy. If x is 0.5 or half, then 1 over x is 2. So now you plot that. Okay, so as you reduce x, it approaches the vertical axis, and what does it do? It shoots off to infinity, right? Okay. Now you go to the other side, and you start with negative numbers. So 1 over minus 1, 1 over minus 0.5, 1 over minus 0.25, and so forth. What happens? It goes off into negative infinity. What is it at 0? It's, either positive infinity or negative. What is it? We don't know. It's undefined. And so that's why we say that the 1 over 0 is undefined, and that's why you punch it into your calculator. It says error. When you do in a program, your program, jumps out on an error and so forth. So you want to avoid singularities. It's harder to do than you think when you're doing a lot of computations. So.
But isn't that infinity? You can call that God.
Now, one thing you can do when you encounter these is you can reformulate your problem. Sometimes you can reformulate your equation so that the singularity occurs in some other place that you're not interested in. So that's one of the techniques. The other thing is you fudge it. You say, well, okay, approximately 0. We're going to divide by something that's a little bit bigger than 0, but it's close enough for government work. So we did that a lot too. Yeah.
Can you just make a comment about singularities and black holes and this issue? How do you connect those two together?
Well, what it means is, so our physical universe is governed by several basic principles. One is quantum mechanics, and the other is relativity. Okay, when you use the equations of relativity, you get singularities. And so what happens is when you use the mathematics to try to understand what's happening inside of a black hole is where something is so dense, not even light can escape. Okay. In fact, matter can't even support itself. So it, according to relativity, it condenses down into a 0. Zero volume. What happens to it, right? Well, what it is the mathematics is breaking down to where it can't tell you, the theory can't tell you what's happening in the center of a black hole, right? Turns out the same is true in the universe, that the mathematics that describe the universe break down when you get to the creation event, I'll call it. You get a singularity. So we'll get into that a little bit. So John's jumping ahead. So fun stuff. Hope your head didn't explode. All right, here we go. Welcome to part 2. Today we're going to be focusing in on the laws of nature. There's a common belief today that science has kind of done away with the need for God. It goes something like this. Our ancestors were bound by superstition. First they thought that spirits animated the natural world, and then they moved on to belief in gods of the earth, and then mankind developed beyond that to where we believed in a single God who was responsible for all that we saw in the natural world. But now with science, we understand how things really work, and we really don't need God anymore. We've done away with superstition because we've replaced it with science. So that's kind of the common belief that I think many people hold today. What's kind of odd about that is that the idea of the laws of nature is really rooted in the Judeo-Christian belief in a supremely rational, all-powerful, transcendent creator. So that's kind of what motivated many scientists. They had good reason to do that in the Judeo-Christian belief in who God is and what he's like. And then the idea that you can apply mathematics to understanding the laws of nature, again, is rooted in the idea of man created in the image of God, and therefore being able to some extent, think like God and understand his ways to some degree. So it's kind of ironic in a sense, and so it reminds me of a story I heard a long time ago. It was about some critters who lived inside of Mozart's piano. Those critters had lived generation after generation enjoying the most beautiful music coming from Mozart's mind and hand as it floated through the air, and they always enjoyed it. And so the little baby critters would ask Mommy and Daddy, where's that beautiful music coming from? And they said, oh, that's coming from the great composer. One day, Junior went off and did some exploring. He was an extra bold little guy, curious little guy, and he noticed these big, long things that seemed to disappear in the distance. They turned out to be strings, and he noticed that when at certain notes, certain strings would vibrate. So he said, aha, that's where the music comes. It comes from the vibrating strings. And so he ran off to his mommy and daddy. He says, Mommy and Daddy, I know where the music comes from. It's not really the great composer. It's really coming from these vibrating strings. And they said, oh yes, well that's great, but you know what? What causes the strings to vibrate? Surely it's the great composer. And Junior was happy with that, but the next day he went off exploring further, and then he noticed these great big padded things coming down out of the roof, so to speak, and hitting the strings. He noticed when they hit, the strings vibrated, and so he ran back to his mommy and daddy. He says, guess what, Mommy and Daddy? I discovered where the music comes from. What causes it with the strings to vibrate? It's those great big pads that come down from the ceiling. It's really not the great composer. And his parents said, well, yes, but what causes those hammers to come down? Surely it's the great composer. And so on this went as each day Junior went and explored a little bit more. And as you know, the inner workings of a piano are quite fascinating, as you have the hammers and pads and all sorts of stops and pins and stuff like that going all the way out to the keys and so forth. And so as he got more and more insight, he kept running back and telling his parents, and finally he convinced his parents, you know what, there must not be a great composer. The music is just all these hammers and stuff hitting the strings and so forth, and that's what causes the music. There really is no great composer. So they settled down into that contented knowledge, and yet they weren't quite as happy as they were before. And yet all the time, this most beautiful music was floating through the air as Mozart sat at the piano playing away on the keyboard. So the moral of the story is, just because you explain something doesn't mean that you explain things away. And that's the way it is with the laws of nature. There's a beauty and there's a wonder in the laws of nature that are hard to explain apart from God. They point to God. I'll give you some examples. So here we have Kepler's laws of planetary motion. Kepler lived in the 1600s, and he discovered that the planets went around the sun in an elliptical trajectory or path. So if you take an ellipse, it has two foci. That's kind of how you define an ellipse. And at one of those foci was the sun, and the planet zipped around that end. Kepler discovered not only is it an ellipse with the sun at one of the foci, but also the planet swept out equal area in equal amount of time, no matter where it was on the ellipse. And lastly, he discovered there's a relationship between that long axis from left to right and the speed at which it went around the sun. And so there was this relationship now that applied to all the planets. If you knew the orbital parameters of a particular planet, you could predict how long it would take to go around the sun. And so Kepler's response to this discovery was wonder at the omnipotent God who created things in such a rational way and had given man the capability to understand that. So he didn't see it as driving God into the shadows, so to speak. Rather, he saw it as pointing to God. Well, same thing with Isaac Newton. Of course, Newton is famous for his law of gravitation, but also his laws of mechanics. My favorite, force equals mass times acceleration. It turns out Kepler's laws are derivable from Newton's laws. And the wonder and beauty of Newton's laws is their breadth of application. We use them all the time at work. We use them in structural analysis to predict how stress will flow through a part, when the part will break, how it will deform, how it will shake. Our mission designers use the Newton's laws to design trajectories for getting to the moon and putting people on the moon and back. You can drive all that from Newton's laws. And then, of course, it's used to describe the flow of air around a wing and the flow of water through a stream and the motion of waves on the ocean. Just the depth and breadth and power of Newton's laws just has a real beauty about them. And then in 1915, Albert Einstein proposes a theory of general relativity as stated in his field equations. And those field equations relate time, space, matter, and energy. And those four quantities are tied together. It really shows up in the area of the very large on the scale of the universe and the very high speed as you approach the speed of light. And that's where you really begin to notice the difference between that and Newton's laws, which are a special case of Einstein's field equations. General relativity has been described as the most beautiful of all the existing physical theories. And it's used in correcting the time codes that we get from GPS satellites. You have to take into account Einstein's theories when you're correcting the trajectory as your spacecraft are heading to the outer planet. And of course it describes black holes. So the depth and breadth of those equations is just incredible. And then there's the mystery of quantum mechanics, the laws of quantum mechanics. And here you see Schrodinger's wave equation. The predictions from quantum mechanics are very bizarre, shall we say, and very counterintuitive, but they apply at the very small level in a region of which we have no intuitive feel. And it turns out that the laws of quantum mechanics explain how atoms can exist. They explain the periodic table and the differences between the various elements. They explain colors, how color is produced, how we perceive color, how our eyes process the color and turn them into nerve signals for the brain. They're used in discerning the composition of stars that are light years distant. So the breadth of applicability of the laws of mechanics are just amazing. And finally, I want to discuss Noether's theorem. It's a mathematical theorem, and it basically says if your mathematical equations have certain characteristics, there's certain implications of that. And it turns out that these physical laws share this property called symmetry. So it turns out the law of conservation of energy really is manifesting symmetry with respect to time. And the law of conservation of momentum is manifesting symmetry with respect to space. And so this whole idea of the beauty of symmetry is kind of a guiding principle for physicists these days. So how do physicists respond to this? I want to read to you a quote from a physicist who was interviewed by Scientific American. The physicist's name is Christopher Search. And here's what he said. Over the years, my view of physics has evolved significantly. I no longer believe that physics offers all the answers. It can't explain why the universe exists or why we are even here. It does, though, paint a very beautiful and intricate picture of how the universe works. I actually feel sorry for people that do not understand the laws of physics in their full mathematical glory because they are missing out on something that is truly divine. The beautiful interlocking connectedness of the laws of physics indicate to me how finely tuned and remarkable the universe is, which for me proves that the universe is more than random chance. Ironically, it was by studying physics that I stopped being an atheist because physics is so perfect and harmonious that it had to come from something. After years of reflecting, I simply could not accept that the universe is random chance. So the wonder and beauty of the laws of nature point to the omnipotent, all-wise Creator God. I also want to point out something else, and that's the utter reliability of the laws of nature. They really don't change. You can count on them, and we count on that all the time because you drive into your garage, you don't worry about the roof collapsing. You step on the ground and you don't expect it to give way. You rely on this consistency. And we rely on it all the time in engineering. When we design buildings and stuff, they're not going to change. Well, why are the laws of nature so reliable? Well, because the laws of nature is actually rooted in God's omnipotence. He spoke the world into creation, and when he spoke, it came to be. And because God does not change, so the laws don't change. Now, if we do have some laws that change, well, it just means there are more underlying, more fundamental laws beneath them. And so it has to do with God's omnipotence and his omniscience. So I have this wonderful quote from the book of Jeremiah. So he's talking to a very discouraged people of Israel. They had expected to have a king on the throne. That king was taken into captivity. And so here's what God told them through Jeremiah. He said, "If I have not made my covenant with day and night and established the laws of heaven and earth, then I will reject the descendants of Jacob and David my servant, and will not choose one of his sons to rule over the descendants of Abraham, Isaac, and Jacob." And of course, God did fulfill his promise, just as he said he would, and he did send his son to save the world. So you can count on the laws of nature, and I think it's kind of interesting. God's moral laws, we think maybe we can get around those as if they're any less certain. We have free will. We can choose whether to obey God and do what he wants us to do, or we can violate them. But there are consequences if we don't, and you can't get around that. When we do mishap investigations, something goes wrong, like a shuttle failure or a failure in a facility or something like that, we do a detailed investigation to find out what were the causes of the mishap, what went wrong. It never boils down to, well, the laws of physics are different, they changed. We never blame the laws of physics. It always comes down to human error. Somebody didn't understand how things work. Somebody didn't design something right. Somebody didn't make things right. Somebody didn't inspect something right. So failures always go back to human error, not to the laws of nature. So given the laws of nature, are miracles possible? Well, that's really a philosophical question, not a scientific question. You kind of need the laws of nature as a backdrop in order to give the word miracle any kind of meaning, because miracles are where something from the outside comes into nature and interferes with it, so to speak. It breaks the chain of cause and effect. So are they possible? Well, of course they are. They're possible for him who spoke all things into existence. So this picture of Jesus, he was with his disciples on the storm on the Sea of Galilee, and they were scared for their lives, and Jesus stood up and he spoke to the wind and the waves, and he said, "Peace, be still." Immediately everything became calm, and the disciples were just flabbergasted at the power of Jesus. And yet he was the one who spoke everything into existence. And so when he told them to be quiet, to be still, they had no choice but to obey him, and they quieted down. So you really can't take Jesus seriously without taking his miracles seriously. They go hand in hand, and he said his miracles point to him and to who he is. He is God's Son, the Son of God, and the one who spoke everything into existence. So I sometimes wonder when I contemplate the miracles of Jesus, what really happened there? I mean, what happened to all that energy and all that momentum when those waves ceased and when the winds died away? What happened to them? Did the big storm show up on the other side of the world, or they just kind of disappear altogether, or what? Or when Jesus healed the eyes of the man who was born blind, what happened? It's not just fixing retinas and nerve connections and stuff. There's reprogramming that has to go on in the brain so that when the man opens his eyes, he can perceive and understand what he's seeing. So it's just amazing what is involved in the miracles, and therefore that points to Jesus' power. And what about raising someone from the dead? Jesus raised people from the dead. Can you imagine what happened when he did that? And then he himself came back from the dead. So are miracles possible? Yes, they are, to him who spoke all things into existence. Now, given the laws of nature, does God answer prayer? And all I can say is that Jesus taught us to relate to God as our Father. And he told us to ask. And he said if we asked, we would receive. He said we could have confidence that he hears our prayers, and God delights to answer us when it is for our good. And of course, certainly you see examples of this in the Bible. So when I ask for something, am I asking God to interfere with the laws of nature, to frustrate those meteorologists, to have the storm hold off, or what? So I don't know how it works, but I do know that we are to relate to God as our Father. And part of that is a relationship in which we ask and receive. And God the Father also asks and receives from us too. So it goes both ways. And I would like to say too that the most fundamental need that humans have, it's in the heart and it's in the soul. And I've seen many times where God did miracles in people's hearts and minds in answer to prayer, and where God displayed his supernatural power in transforming people from the inside out. Okay, with that, I'm going to move on to a slightly different topic, and that's the universe. Did the universe have a beginning? And of course, this has been debated throughout the ages. The Hindus believe in an eternal cyclical universe, so there's always been this debate. Judeo-Christian point of view says that God created all things, so he's the origin of all things. So what's the fundamental issue? The fundamental issue is to what or to whom do we owe our existence? If the universe has a creator, then we owe our existence to that creator. This picture is the Hubble Deep Field, the Hubble Space Telescope in space, stared at an empty patch of sky for on the order of 100 hours total. And this is what it saw. All those little fuzzy patches you see are actually galaxies. They're island universes. You see this inset of the Andromeda Galaxy. Andromeda Galaxy is our sister galaxy. So it's right next to us in astronomical terms, and it looks somewhat similar to us. You can see those lanes going around spiral form that are lanes of dust created by stars. You see all that fogginess. Those are unimaginable quantities of stars whirling around with planets around them. And of course, all the lights that you see that look like big stars, those are actually in our galaxy. We're looking through our galaxy to this distant galaxy, our sister galaxy, and the fog is made up of individual stars. And now we look at the universe as a whole, and we see galaxy after galaxy after galaxy on into the distance. And it turns out that the farther away the galaxy is from us, the farther away it is fleeing away from us, and the younger it looks. And this points to a beginning of the universe. Okay, so before modern science, these arguments were going on, and the Kalam cosmological argument was one of those arguments about the universe having a beginning. It said basically whatever begins to exist has a cause outside of itself. Just kind of common sense, right? And then the universe began to exist. Well, how do we know this? Well, it turns out that there are certain logical contradictions that result if you assume that the universe is infinitely old. So if the universe began to exist, then the universe has a cause outside of itself. Who could that be, or what could it be? So if the universe has a cause, and an uncaused personal creator of the universe exists, who without the universe is changeless, immaterial, timeless, spaceless, and enormously powerful. But in the 1700s, a philosopher by the name of Immanuel Kant, sometimes called the father of modern cosmology, proposed that the universe was eternal. He felt that it made sense both philosophically and scientifically, that you had to assume that the universe had always existed, and if you didn't, it took the foundation out from underneath science. So basically he was pushing God off into the shadows, so to speak. The universe has always been here, but there were some problems with this that people pointed out. One of them is Olber's paradox. It was proposed by him in 1823 that if the universe is infinite in space and time, then the night sky should be bright, not dark like it is. And that's because everywhere you'd look at the night, you'd eventually bump into a star. So wherever you look, there'd be light. So that was one issue that was raised. Well, gee, what's the solution around that? And then there was Rudolf Clausius, who proposed in 1860 the law of entropy. It basically said that all things in a closed system tend toward disorder, and that's the natural flow of things. The universe is running down, and it's heading toward this endpoint called thermodynamic death. But it also means that if you go back in second time you reach a point of zero entropy, where you have supreme order, and that would mean the universe had a beginning. I remember a college professor told us, I think when he was talking about the law of entropy, he says, one thing I can tell you is that the universe had a beginning and the universe will have an end. And I believe this is what he was referring to. But physicists, cosmologists really did not accept it, as still the prevailing view was that the universe was infinitely old. And then Einstein came out with his field equations. Well, one of the consequences of the field equations is that the universe is either expanding or it's falling back in on itself. Either way, it started out as a point. And so Einstein introduced something called the cosmological constant, and that's so he could show a steady state universe that was consistent with what cosmologists believed at the time. The problem is it didn't really conform to observations. And so we have this guy, Reverend Georges Lemaitre, who was a Roman Catholic priest and physicist and theoretician. He said the consequences of general relativity is that the universe must be expanding, and that would explain why nearby galaxies are moving away from us. And then Edwin Hubble used telescopes, spectrometers, to measure the Doppler shift of galaxies. He and Lemaitre came up with their law jointly. The galaxies are receding from the Earth, and it's approximately proportional to their distance from the Earth. So the farther the galaxy is away from us, the farther it's zipping away. And the implications are, of course, that as you run the video backwards, it all begins in a point. Everything comes back together. And that means the universe had a beginning. Well, how did this go over? It didn't go over well at all. Here's a quote from Arthur Eddington, a theoretical physicist of the last century. He said, philosophically, the notion of a beginning to the present order of nature is repugnant. Another gentleman by the name of C.F. von Weizsäcker, the physical chemist, he said, the view that there might be an age of the universe is not science. The infinite duration of time is a basic element of all scientific thought, and to deny this would mean to betray the very foundations of science. So the theory received quite a bit of ridicule. In fact, the name Big Bang given to this theory was actually a derogatory term given by people who were skeptical of it. Well, one of the alternate theories was the steady state theory of the universe. Yes, the universe is expanding, but as galaxies get further away from each other, empty space opens up and matter spontaneously appears. And so the universe could have been expanding forever. So that was called the steady state theory of the universe. But in 1948, it was predicted that as a consequence of the Big Bang theory, basically as a consequence of nucleosynthesis, the combining of electrons and neutrons into hydrogen atoms as the universe cooled off shortly after the beginning of the universe, that this would produce a background radiation. So this radiation was first observed in 1965, and it was considered a major confirmation of the Big Bang theory, effectively killing the steady state universe model. So the Big Bang theory is pretty much universally accepted among physicists today. So what is the cosmic microwave background radiation, or the CMB? It's a wall of light emitted when the visible universe was 100 billionth its present size. That means you and I would be closer by a factor of 100 million than we are now. Unimaginably close. Because of it being so small, the temperature was extremely high. It's estimated to be 273 million degrees. But because we're fleeing away from it due to the expansion of the universe, it looks to us like it's only 2.7 degrees above absolute zero. So that means it appears to us in the microwave portion of the electromagnetic spectrum. And it's uniform in all directions to 1 part in 100,000. So if you had eyes to see down in the microwave region of the spectrum, it would look like this. Think of this as the Earth flattened out into the shape of the sphere. You've seen maps like that, except you're in the middle of the sphere and you're looking outward. So in a sense, we're looking at the universe as it's flattened out into a big oval, so to speak, and it would look uniform to your eyes, to 1 part in 100,000. NASA sent up several spacecraft to actually map the minute variations in this background, and they get a picture that looks something like this. There is variation, but they're very minute variations. From these variations, they can test various theories about what happened in the early stages of the expansion of the universe and infer certain things about the origin of the structure in the universe that we see today and so forth. So now I want to show you one other thing, introduce you to these gentlemen. You probably know Stephen Hawking, his co-worker Roger Penrose. They developed the Penrose-Hawking singularity theorems. And what they did is they proved that if general relativity is true, the cosmic expansion began from a point of zero volume containing all the energy and mass of the universe. That's called a singularity. So the implications of that is that space and time had a beginning. Not just space, but time itself had a beginning. So what would happen before the beginning of time? Well, that's beyond our ability to understand, but the time had a beginning, and so did space. And the Big Bang was, in fact, we think of a violent explosion, but in fact it was an extremely smooth expansion of space-time itself, space and time being coupled together. And it was an event of extremely low entropy, the exact opposite of black holes. Black holes result in extremely high entropy. And lastly, you look at the parameters that govern the universal constants that cover the rate of the expansion of the universe and so forth, that there's just a very narrow band at which the universe that we imagine today can even exist. And the fine-tuning that's required is 1 part to 10 to the 10th to the 123rd power. This is an absolutely unimaginably large number. It cannot even be physically written down in the universe. But that amount of fine-tuning is required in order to obtain the kind of universe in which we live. So what does that point to? Here's a reaction of a journalist who listened to a talk on this. I certainly didn't give it, but somebody much more knowledgeable than me. What if God is real, inexorable and majestic, impossible to escape? Not the wisp of hope you feel for a happy outcome when your airplane hits some turbulence, but the vertigo which you feel looking down on the Grand Canyon, which seems somehow to be sucking you in. So this points to a transcendent creator, someone that we cannot escape, someone who has knowledge beyond our wildest imagination, someone who has unlimited power, wisdom, and so forth. So it points to basically to the God of the Bible. But this can be a terrifying thought. Just think, you cannot escape God. There's no way. He's closer than breathing. So let me quote to you from Isaiah the prophet. He wrote around 700 BC. He said, "To whom will you compare me? Or who is my equal, says the Holy One? Lift up your eyes and look to the heavens. Who created all these? He who brings out the starry host one by one and calls forth each of them by name. Because of his great power and mighty strength, not one of them is missing." So God is so awesome. He's so terrifying in a sense because he's so big and we're so puny. We're less than a speck and a speck and a speck of the incredible universe, and that's just a speck compared to God. He's not even aware of us. How can he pay us any attention, answer our prayers, and so forth? And yet, that's not what Isaiah says. Why do you complain, Jacob? Why do you say, Israel, my way is hidden from the Lord? My cause is disregarded by my God. Is he too big to pay attention? If you think he's too big to pay attention, that means you think he's too small. Do you not know, have you not heard, the Lord is the everlasting God, the creator of the ends of the earth. He will not grow tired or weary, and his understanding no one can fathom. He gives strength to the weary and increases the power of the weak. Even youths grow tired and weary, and young men stumble and fall. But those who hope in the Lord will renew their strength. They will soar on wings like eagles. They will run and not grow weary. They will walk and not be faint. So God is outside of time. He's outside of this universe. And yet he is closer than breathing. He can hear you when you pray. He knows all your thoughts. So I say, you go to him. So next week, we're going to discuss the design of life. Thank you. While I wait for people to come in, I thought I'd like to explain this picture a little bit on the screen. So this is a telescope that I sort of finished making a few years ago. It's never really finished, but it's ground the mirror when I was in college. Well, many years later, after I got married and had kids, one of my kids who's standing behind me just on the edge of the screen on the right, his name is Joseph. He had read a book by Isaac Asimov on the inner planets, and he was enthralled with Venus, and he had read about this once-in-a-lifetime event that was going to happen in 2012 called the Transit of Venus. And so that year, he said, it's going to happen in June. He says, "Dad, could you finish your telescope so we could watch this event?" And I says, "Okay, well, I'll try." Well, it happened to be a very tough time for me. It was I was under a lot of stress and at work, and I was having some serious health issues. And I just felt I couldn't do it. I told Joseph, I can't do this. I'm sorry. we'll go watch it, but we can't watch it with a telescope. And he said, Daddy, I'm going to pray. He was not giving up. And so I kind of felt like, well, gee, I better finish this. So somehow God gave me the strength to finish the telescope. But one of the things, you can see the little silver shield on the end. That's to keep your eye from burning out when you look through the telescope when it's pointed at the sun. Turns out there was a big run on those that year because of this big once-in-a-lifetime event. So I ordered the stuff, and I wondered if it was going to come up in time. It showed up like a day early or so before the big event. So I quick ginned up a holder to put on the end of the telescope, and I finally, on the day of the event in the morning, I took it out to look at the sun, and, it was cloudy. It's like, oh my goodness, how on earth are we going to watch this once-in-a-lifetime event when it's going to be cloudy? And the weather forecast, as I recall, was not that good for Cleveland. Well, wouldn't you know that the clouds just parted in time. I could test out my shield and everything worked. So we packed up the car and went down to Edgewater Park and got just wonderful views of the transit of Venus. And we had a big line forming behind the telescope of little kids wanting to take a look. And you'd see my toolbox down there that kids would stand on in order so that they could get high enough. So anyway, that's my story. All right. Well, time is fleeing fast. Had a couple of things I wanted to do, kind of follow into the video. I didn't want to mention, so there's 4 of these videos, so that's the second one. I have lots of cards. I ordered 100 of them for this class, so if you want to take multiple cards and hand them out to people, you're welcome to take what you would like. This could be a resource for you as you talk to people. With this, you can watch it with your cell phone. At the end of the quarter, I'll send you an email with URLs in it so you can forward that to the folks. Anyway, take as many as you want within reason. All right, so let's go back. What on earth could we follow up on that? I don't know. We covered 2 major mind-blowing topics in this. And so as a result, I'm going to have 2 hours of follow-up. So next week, we're going to do the first half on the laws of nature. The next week after that, we're going to talk about astronomy, cosmology, and the glory of God. So that's the plan. So we're going to install that guy. So I wanted to go back to the first part of the video. I gave this little parable, which I got from somebody else, by the way, many years ago. Adapted it to modify it to my own uses. But anyway, so the question I think it brings is, what does science really explain? So, this little mouse is, what a critter, he's probably, I don't know, it's a bug, probably. He's going through and he's making all these discoveries, but what is he really discovering? He's discovering how the piano works, right? How it works. It doesn't explain the origin of the music. It doesn't explain the music. So why is it so beautiful? Where does it come from? All this kind of stuff. Piano with no playing, it was just sitting there and didn't do anything. That's the way the laws of nature are. The laws of nature really describe how nature works, but they don't really make anything happen. What makes things happen? What makes things produce this beautiful music that we see? And so it is with science. Science is a wonderful thing. You can study creation and be in awe of the great engineer who created the system, and you can still miss out on the beautiful music. So science really explains a very limited part of our own experience and what's important to us. It doesn't explain love. It doesn't explain morality. It doesn't explain philosophy or literature or the arts, anything like that. In fact, science doesn't even really explain science, right? If you want to explain science, you have to go outside of science in order to explain it. You have to go into philosophy. Yeah.
I stumbled on this question I can't figure out. Why do so many countries spend billions and sometimes trillions of dollars looking at galaxies 15, 20 billion light years away? They put all that money into trying to find something out there. Why don't they put the money back here to how much gallons could you get out of a diesel gallon or a truck or something like that? That's not a funny question. I don't know what are they looking for at 20 billion light years out there? I don't know what's the point.
Well, I think it's in the nature, the way God has made us, to be curious. We want to understand the world around us. So this really comes from that innate desire that God has put in us to understand the nature of the world around us. And there's nothing wrong with that, okay, but what about the resources? Yeah, it takes a lot of money, not compared to Social Security, to other stuff. So my aunt was telling me, why are we sending, all these men in space when we could be spending this money on our crumbling infrastructure? Of course, she knew I worked for NASA. She also knew I was retired. Well, everybody at NASA, I think, thinks about that. But it's, when you look at it another way, okay, this is kind of an outgrowth of the invention of a lot of technology. So we invented rockets, we invented life support systems, and all this kind of stuff. Okay, so you want to defund the space program, let's get rid of our weather satellites and show us where hurricanes and tornado systems are formed, right? Let's get rid of GPS that helps us find our way. Let's get rid of these satellites that tell you where forest fires are. Let's get rid of our communication satellites so we can't talk to people real time, across the world and stuff like that. So, if you look at the cost of the space program versus the benefits of it, there's a huge disconnect. So I don't regret too much. Now I do realize that there's humanistic philosophies that drive a lot of this, right? But my feeling is you're learning things, and it's going to be fun. So, yeah.
Yes, I can just talk about this concept called the God gap that many people who argue against Christians and otherwise, just so that people understand that term and how to respond to it.
So God of the gap we refer to God when we can't explain something, right? So you see something in nature, and scientists can't come up with something, a good theory that explains it. So you say, oh, that's the God of the gaps, right? That God did that. God did that. And then what happens is in science, science progresses, and then they find something else that turned out to explain that phenomenon. Okay, well, the gap is filled. You don't really need God to explain it. So that's the hot idea. So Christians are often accused of referring to the God of gaps when using science to point to God. But I don't think they're looking at the big picture. Right? They're not looking at why do all these laws exist to begin with. Why are we even rational creatures and all this kind of thing? Yes?
There's a similar story that I'm familiar with of one who on the piano, which I like repeating to people. Same sort of thing. Put a painting on the wall, and you tell science to come in and say, okay, tell me everything you can about this painting. Science will come in and say, okay, oh yeah, look at this wood, that's from a popular tree in Africa. Look at this canvas, and it was very popular fabric out of a factory in Paris at the turn of the 20th century. This paint is from the indigo plant, and so on and so on and so on. And they'll just rip it apart and they'll give you everything you need to know about it. But the two things that they'll never be able to prove is who painted it and why. That is only done through revelation.
So we saw this, the first class I showed this Venn diagram, what was the domain of silence. So you had area of all truth. Right? I claim that was infinite because it includes truth about God. God is infinite, okay? But then some of that is truth about nature, and then a subset of that stuff about the truth about nature that's amenable to science, that you can learn about from science. That I think in reality that's a very small part of life, that part that's really it's amenable to science. You're going to say something?
As you presented it today, I would say we as Christians should really be embracing the Big Bang, because if that doesn't sound like, and God said, let there be light, and there was light, I don't know what does. But that is not the general feeling about the Big Bang. Do you have a sense for that?
Well, I think we should not be afraid of the Big Bang, whether you're a young earther or an old earther. And I'll tell you why. Because it's science saying there is a beginning. And non-Christians hate it. You read the news feeds on Apple News, all this junk science reporting. Most reporting on science is junk, okay? oh yeah, James Webb Space Telescope is showing there's a problem with the Big Bang, and you have all this kind of notice. James Webb Telescope wouldn't see anything if the Big Bang didn't happen, because it's built on the assumption of cosmic expansion and things in the distance being in the very far infrared region of the spectrum. Okay, so it wouldn't even work. Okay, but it shows that there's a beginning. The universe expanded, according to this theory, expanded from a point. So you run real backwards, we get closer and closer. When you get to where you see that cosmic background radiation, we're actually closer by a factor of, I think I said 100 billion. I mean, that'd be, kind of tight. And that's big. You keep going back further and further and further, That was like 300 some odd million or 1,000 years after the supposed Big Bang. So I think, it points to God. And like I say, non-Christians, atheists hate it. And they're always coming up with alternate theories. And those alternate theories are always being knocked down. Now that doesn't mean the Big Bang is true. It's a thing, it's called the Big Bang theory. Maybe we'll discover something, in the future that, wow, this really doesn't make sense, what else is going on, all this kind of stuff. So it may be the case. But when talking to other people, to people who doubt God as creator, just point to them. Well, this is what science says. It's obvious the universe had a beginning. There's someone to whom we owe our existence. And if we owe our existence to him, we owe a heck of a lot of other stuff too. Okay.
Seems like a lot of the breakdown comes to the concept of time. It's like, yeah, time means beginning, time means end. They can't comprehend someone who holds time in his hand.
Yeah. But you know what? Theologians came up with those concepts millennia ago. I mean, hundreds of years ago. They're in the Middle Ages. They're toying with all this stuff and talked about the beginning of time and all that kind of stuff. Yeah, somebody had a question. You did? Did you?
They're just using semantics.
Yeah.
The left, the liberals, the scientists.
So I would encourage you. I mean, I find this kind of stuff invigorating, but don't put your faith in scientific theories. Don't put your faith in Christ and your faith in God's Word contingent on scientific theories. That's a big mistake. Okay. Scientific theories are always being disproved, superseded, and that kind of stuff. We have enough information, and we'll talk about this next week at the beginning, why I believe the Bible is God's Word, is we have good reasons to believe the Bible is God's Word, but not reference. All this stuff. So our faith is in Christ, and it's in Him, in His person. Yes?
Yeah, I think we as Christians talk about absolute truth a lot, and I think that's good. And the foundational premise in science that absolute truth exists.
Mm-hmm.
But I think we all need to understand all scientific statements are always provisional. These are human statements based on theories that we have developed to explain something. And because everything is provisional, one could also equally say, I believe in absolute truth, but I'm not sure if I can ever actually know it, because we're human, right? And so we may reach it asymptotically, which means that we approach it, but we actually never get there.
Yeah.
I think we need to have a humility, just because we believe absolute truth exists, one should be very careful who you actually know.
Yeah. So the absolute truth is found in Jesus. And He will lead us all into all the truth. And there's been so many, if you look so many times, theories are superseded, amended, all this kind of stuff. You go back, people who built whole careers, doctorate professor who's been a lecturer all the time. And then his students come along, disprove all that he built his career on, and then they move on, and then their students will probably disprove some of what they, built their whole lives. And I mean, that's scientific progress. It's provisional. So. All right, well, let's pray.